One topic that comes up here and there throughout the course is domain of a function. So in other words, what we're expecting is that when we give you some kind of a function, and it's not like any kind of function, we're looking at sort of a select representation here, but when we give you a function, we want to know what the domain is, because frequently that would be a concern. And so in this video and in a couple of other videos that are related, we're going to talk about how to find the domain of a function. And right out of the gate, it's important to understand that this is much easier if you can recognize what type of a function it is that you're dealing with. And so I have a list of various types here on the screen, and I will go through several examples in this video and in the videos to come. So let's talk about polynomial functions first. On the screen in front of you here, you can see a typical problem set where they give you a variety of functions and they're asking, find the domain. And so what I'm wondering is, do you recognize any polynomials among these problems here? Because there are a few. And so that's a good example of where we're coming from. We want you to be able to look at a particular function and recognize, okay, that's a polynomial, and therefore the domain is such and such. So working our way down the list here, how about polynomials? What is a polynomial? How can you identify one? And what's the domain? How do you find the domain? Let's take a look. The formal definition of a polynomial is it's a function which is built from a finite sum of power functions with non-negative integer exponents. And you can see some examples on the screen here. F of x, for example, f of x equals 12. Believe it or not, that's a constant function, but it's also a polynomial. It's a 0-degree polynomial. Likewise, g of x, 3/4 of x minus 9, that is a linear function, but it's also a first-degree polynomial. And h of x probably comes closer to what most people think of when they visualize a polynomial in their mind's eye. That's a third-degree polynomial. And the power function components that we're talking about, for example, negative 4.4197x squared, that's a power function. And so when you put a bunch of power functions together, you get a polynomial. And of course, we have the general expression down below, p of x, and that's an nth degree polynomial. So the highest power present tells you the degree, and you can get other information from that, but that's a topic for a different video. Bottom line, if you're looking at a polynomial and you don't have any context imposed on it, the domain is all real numbers, because they're well behaved with whatever you put in. Nothing you can put into the polynomial, no real value is going to make it undefined. And so hence the domain is all real numbers. Now that's not to say, sometimes you may use a polynomial for some kind of an application. For example, you can model the fuel economy of a car at different speeds using a quadratic polynomial typically. And so in that case, the domain is not going to be all real numbers because you have reality imposed on that situation, and that's going to have a say in what the domain is. But if you're just looking at a regular old polynomial, the domain is all real numbers. So if you want to see some examples from the problem set, in this particular problem set right here, you can see that number 47 and number 48 are both polynomials. And they're the only ones from that part of the set. And so the domain of each of those would be all real numbers, which if you write it in interval notation, would be the interval from negative infinity to positive infinity. And so again, that would apply for both number 47 and 48. Let's talk about other kinds of functions. Next up on the list would be rational functions. Let's talk about those. So here are some examples of rational functions. And if you kind of step back and think about, what do they have in common, each one is a ratio of polynomials. And so that's the formal definition of a rational function. It's a polynomial divided by some other polynomial. And our primary concern when we're looking at a rational function like this is that we don't want the denominator to be 0. Because if it is, it causes the rational function to be undefined. Division by 0 is undefined. And so if you have a 0 value in the denominator, it makes the function undefined. And so if you're looking for the domains of these functions, here's how you'd go about finding them. For the first function there, f of x is 1 over the quantity 2 minus x. It's like we were saying, we want the denominator to be non-zero. And so that means that we want 2 minus x not to be 0. Now, even though we're using not equals here, it basically performs the same function as an equal sign in terms of how we treat it when we're solving this equation. And so if you were to add x to both sides, you would have your answer. We don't want x to be 2. So the red circle that I put around x with the arrow is my way of indicating that I'm moving the x to the other side and changing the sign, or if you will, I'm adding x to both sides of that equation. And so of course the result is that 2 is not equal to x. And so if you want to state the domain, you can state it a couple of ways. You can use what we call set builder notation, as you see on the left, x such that x is not equal to 2, or you can put it in interval notation, which is probably the more common way of stating it. So we're saying here that you're going to take those two sets, the interval from negative infinity to positive 2, and then the set from positive 2 to positive infinity, and you're going to put them together with a union symbol. And the reason I'm using round parentheses on the 2 is to exclude it. So either way you slice it or dice it, that's our way of saying everything but 2 is the domain. Let's look at the next example. So we're going to look at the function g of x here, which is x squared plus 1 quantity divided by quantity x cubed minus x. And again, we want to know what's the domain of that function. So let's take a look. Now this one is a little bit more complicated than the previous example, and you might notice that the denominator can be factored. The numerator actually cannot be factored. That's a sum of squares, and if you want to factor it, you have to use complex numbers. So when we say not factorable, we're saying it's not factorable over the reals, because we're dealing with real numbers here. So anyway, probably the first thing you'd want to do would be to get the denominator of g factored. And if you know what you're doing, you probably could pause the video and do that. In fact, why don't you see if you can match me on that? Go ahead and pause the video right now and see if you get the same factorization that I get. So down in the denominator, hopefully you would notice you have a common factor of x, and if you extract it, you're going to have x times the quantity x squared minus 1. And of course, x squared minus 1 is a difference of squares, and that can be factored as quantity x plus 1 times quantity x minus 1. So once you have the denominator completely factored, now you're in a position to talk about what the domain is going to be. You can do the following. So we set the denominator not equal to 0, and if you apply the usual analysis to that, you're going to have x not being 0, because you can see that if x is 0, then the rest of the denominator is going to be 0 as well. And likewise, x cannot be positive 1 or negative 1. So those three values are off the table. And therefore, we're in a position now to tell you what the domain is. It's basically everything but 0 or positive and negative 1. And the way we're going to say that, well, we'll do the same thing that we did before. So we've given you the domain using the set builder notation, and that's our way of saying everything but 0, negative 1, or 1. And we've also given the domain using interval notation. So you notice that for every value you have to exclude, you end up using a union symbol, because you're going to have disjoint unions that have to be glued together, if you will, using interval notation. And so here we have the interval that is excluding negative 1, it's excluding 0, and it's excluding 1. It's everything else. Let's look at the next example. Let's take a look at h of x, the function down there at the bottom. Now there's a little bit more going on here in h of x than meets the eye, and so that's why this is such a rich example. If you feel like you know what you're doing, you could pause the video and you could try it yourself and see if you match me, but let's take a look at it. So in this case, hopefully you'd notice that both the numerator and denominator can be factored, and so that's the first order of business. We want to get those factored and then take stock of what we've got. So as you can see, the numerator is the difference of squares, and that's going to factor as the quantity x plus 2 times x minus 2. And the denominator is just a regular old quadratic. You're looking for two numbers that multiply to make negative 10 and add to make positive 3. And so your choice is pretty limited. It's going to be x plus 5 times x minus 2. Now hopefully you would notice that you have a common factor in the numerator and denominator which can be canceled, namely x minus 2. And so if you do cancel that, you can see that the quantity simplifies to be x plus 2 over x plus 5. So you might think to yourself, so the domain would be x is not negative 5, right? And I would say, well, actually it's not. And the reason is because you cannot perform that cancellation that we just did unless the rational expression is well defined. And what that means, practically speaking, is that you can't cancel when the denominator is 0. And so that means that there are two values that have to be excluded here, namely negative 5 and positive 2. And so that would be the domain for this particular function. Let's put it down. So in other words, before the cancellation took place, that's where we're looking at our denominator and using it to determine the domain. And so if the quantity x plus 5 times x minus 2 is non-zero, that would mean that x cannot be negative 5 or positive 2, and therefore the domain would be x such that x is not negative 5 or positive 2. If you put it in interval notation, you can see that down at the bottom, and that's probably the way we'd want the answer. So keep in mind, canceling something like that doesn't mean it's no longer a concern. In order to keep the original function h of x well defined, in order to do that cancellation, then we need to have the domain as you see it. Let's look at something quickly in the problem set. Now, of the functions that we have here in this particular problem set, from number 47 to number 62, which of these are rational functions? Well, hopefully you'd notice that number 49 is. Likewise, number 50, number 51, 52, 53, and 54. Some of the other functions in there look rational, but they are actually sort of a hybrid, and so we'll have something more to say about that later. But hopefully you'd be able to field any of these with relative ease, and the answers would be very similar to what we would see in the video earlier. If you have any questions, please feel free to drop me a line. Otherwise, you can go on to the next video and we'll talk about some other kinds of functions and how to find their domains.